Okay, welcome back, everybody, from the reading week. So today we will continue our lectures on parameter homotopies and these parameterized polynomial systems. So I'll remind you all of what's going on in that story today. I will remind you all of the main theorem that really makes all of this work. And then we will continue with examples, some of which we've already seen a little bit of in the previous lecture, specifically the total degree parameter homotopies, which we've seen in many disguises throughout the course, the sparse polynomial system parameter homotopies, which are my favorite, and the witness superset parameterized polynomial systems, which are arguably the most important ones for the field of numerical algebraic geometry. So our main theorem is the so-called parameter continuation theorem. Does anybody remember what this is about? You know, among friends. Jacob, you're raising both of your hands.
I mean, I can answer it.
What's it tell us?
Tells us that polynomials can be thought of as, or homotopies can be thought of as a homotopy between different parameter sets based on degrees of polynomials. That's a
Yeah. That's the spirit of it. It's really general. It says that if you have a square parameterized polynomial system, that there's some well-defined number of solutions to the generic case, where a number of solutions means number of regular zeros. Okay. So I'll write that up on the board. Where are we working? So working in polynomial ring with some parameters considered as coefficients. And the big condition is that you have a parameterized polynomial system which is square. So as many equations as variables. This says nothing about how many parameters there are. It's really just about the variables. So this has to consist of n equations, n variables, and then say k parameters. Extra credit for this next homework assignment. Show me where this fails if you don't use a square system. So give me a counterexample to the parameter continuation theorem, which justifies the need to have a square system. Okay, so that's the setup. So what's the conclusion? If you take anything in this parameter space, it has some number of solutions. Specifically regular solutions. And this number, of course, can change. So you saw that in the first one. In pretty much the simplest polynomial system you can think of, namely a univariate quadratic, this number changes depending on what parameters you choose. And it's supremum of these, and you give that some notation, call it capital N, then we can draw some conclusions. Find N of Q and N. And the conclusion is this number is finite. And there exists a proper subverity calling delta, living inside the parameter space, such that as long as I avoid that variety in my parameter space, that supremum count is the actual count. Any questions about that? I encourage you to try to break this in several ways on your own. As you should whenever you see a theorem, I think. And then convince yourself that you're having a really hard time breaking it because it's true. It means it really doesn't matter how wild this parameterized polynomial system looks like. As long as it's square, this holds. Right? So y'all thought a lot about counterexamples in your last homework, or examples. You know, these paths going to infinity or landing on a positive dimensional component and all of that. And I saw some great ones. I saw some people chose polynomial systems where the polynomial was just repeated over and over again, right? So, and think about this theorem in the context of systems like that. Really is wild. What happens in that instance is that n is 0. No, sorry, scratch that. In the basic instance of repeating a polynomial, so like having a bivariate polynomial and just repeating it twice, then the answer is 0. Because there are no regular solutions. Do we remember what regular solutions are? Okay, so regular solutions are solutions where if I plug them into the Jacobian of the system, I get an invertible matrix. That is stronger than being isolated, strictly stronger than being isolated. If you have a regular solution, then you are an isolated solution. But if you're an isolated solution, you may not be a regular solution. Hey, a face on Zoom. Hello, Prajwal. So
Yeah.
good to see.
Sorry, I almost forgot that I had a lecture today. Sorry.
Oh, no, it's okay. Yeah. Deep in the research, I'm sure. Okay, so this is the parameter continuation theorem. Okay. And the picture that goes along with this, that you'll see me draw over and over and over again. Like this. But up here, we have our parametrized polynomial system, which you can think of as a polynomial system in the variables x with parameters p. But you could also think about this as a single polynomial system in the variables x and p. Right? And in that case, you get some subvariety of the complex numbers raised to the n plus k. But you should really think about it as tracking the solutions and the parameters for which these solutions are solutions of the system when you plug in these parameters. And then, so this is called an incidence variety. Because it tracks the incidence between the solutions and the parameters. And so at any point Q here, let's say a generic point Q, the fiber of the map which forgets about the solutions, the fiber over Q, I'll just throw in a little box here. Has n isolated points in it, generic. Now there might be positive dimensional components and stuff like that. But ignore those. There might even be solutions with multiplicity, which are isolated but not regular. Which means that this map pi is generically n to 1. So there's generically n points in the pi. Do you remember what generic means?
That it holds for all but a finite amount of.
Well,
It
Yeah.
avoids the proper subvariety.
yeah.
Okay.
Yeah. So again, Spirit is totally correct. And as long as the parameter space is one-dimensional, right? Like we've seen in so many of our homotopies where it just depends on t, that's right on the money. But now we have parameter spaces which are going to be huge dimensional vector spaces over C. We'll see. And so a property being generic means it holds for all points except for those that might be on some proper subvariety. So it's actually in this case and in this setting and in this course, it's strong. It's stronger than being a set of measures here. It is really inside an algebraic variety. Okay, so for example, the rationals have measure 0, right? However, those do not belong to a proper subvariety, as you showed in your first homework. And so what is that proper variety? Well, it's the delta that was guaranteed. might be funky, might have some weird things going on. In general, it's incredibly complicated, is what the intuition you should have for this is. In the univariate quadratic case, it's just a parabola, really. And so it's simple enough there. But as you work into more real world problems, either coming from applications or from theory, pure math, right? You're going to see that these spaces become really, really large. And that does not inhibit the computational prowess of numerical algebraic geometry at all. You don't, so computationally, you shouldn't really care too much about how big the parameter space is, because you can always restrict to just a line segment to go where you need to, and then the parameter space is one dimensional. Okay, that's the setup. Any questions? That's our review. Parameter continuation theory and the general setup of a parameter. So if we have a system like this, we can perform homotopy continuation to any other instance in exactly the same way we did before. For example, you could just restrict to a straight line homotopy between those points. And that works even if you're approaching something that is on delta. However, what you know is that on delta, you might have some multiplicity structure, which is not generically there. You might have some positive dimensional components, which are not generically there. And you might have some solutions flying off to infinity as you approach. Off. You might have something being nice and well behaved. You might have two things going to the same thing. And you might have this point lying in the limit on some positive dimensional component. So this is the parameter continuation set. And this is how I encourage you to think about numerical algebraic geometry moving forward. And it is worth you taking the time to recast what we've done in the multivariate continuation setting and the univariate continuation setting into this framework. Are we ready for examples? Okay. Speed things up a little bit now for the examples. Example 1. Whole degree systems. Fix a degree sequence. And consider a parameterized polynomial system with each monomial in I of degree less than or equal to di, given its own parameter. In other words, f1 of x and p looks like some all alpha such that size of alpha is less than or equal to 1 of p 1 alpha x to b. Nth element of this polynomial system, the nth equation, is the exact same thing. We're just including new parameters, and this monomial set is allowed to have degree of n. Oh, D. So maybe that would be. That's the total degree system. It parameterizes all square polynomial systems with that degree sequence. Example. Equals 2, 1. F1 is like P, I'm using P1, 0, 0 plus P1, 0, 1 plus 1, 0 plus P1, 0, 1 y plus P1, 2, 0 x squared plus P1, 1, 1 x y plus P1, 0, 2 y squared. And F2 equals P2, 0, 0 plus P2, 1, 0 x plus P2, 0, 1 y. So we have 6 plus 3 equals 9 parameters. And the n, the number of generic the number of generic regular solutions for this parameterized polynomial system as guaranteed by the parameter continuations theorem is what number? How many solutions does this polynomial system generically have if I just randomly plug in complex numbers for the PI alphas? 2. Why?
It's the product of the degree.
It is the product of the degrees. I agree with that. And what is that theorem? Base. So the computation, the determination of these capital N's for a given parameterized polynomial system, it's not always easy. And simply determining one of these N's could be a theorem that gets named after you. Univariate polynomial system solving looks like this as well, just the degree sequence is just one number. Example 2. Sparse systems. Instead of fixing degrees, we will fix much more explicitly a collection of monomials appearing in each polynomial. Each AI is a subset of n natural numbers. So the first polynomial is just the polynomial with generic coefficients whose monomials appearing are indexed by the exponent vectors in A1. A1 might look like maybe A2. Somebody is drilling in the room next door. Lovely. Okay. So here's an example. I've given you two supports represented as subsets of the integer lattice. And each dot I've written here indicates a monomial that should appear in F1, and each dot that I've written here indicates a monomial that should appear in F2. And you should ask, okay, well, if somebody gives me these, what is this capital N guaranteed by the parameter continuation theorem? And you don't just get a theorem with one name, you get a theorem with three names. Indeed. So looking at this theorem, if you don't remember from last time, there's at least two things you should be concerned about. The first is, what the heck is mixed volume? And the second is this C star, so the C star to the n wasn't in the parameter continuation. So this doesn't seem like a direct establishing of one of these capital N's from the parameter continuation theorem at first glance. The mixed volume is not very difficult to understand in two variables. In fact, it's just a ton of fun to compute these things in two variables. In more variables, it's a bit more complicated, but I'll give you a formula anyway. So. Sorry about the board work here. So I'm moving a goalpost. And I'm saying the mixed volume of a collection of supports is the same as the mixed volume of the corresponding collection of polytopes you get when you take all of those convex holes. So here A1 is 3 dots. But P1 is this polygon. It's the convex hole of those 3 dots. The smallest convex body containing those 3 dots. A2 is these 3 dots. But P2 is the polygon. Right, the convex body of those polygons. All right, Taylor. Well, what is the mixed volume of a collection of polygons or collection of polytopes? It is an alternating sum of volumes of polytopes. And those polytopes appear as sums of polytopes. So only more questions at this point for you. So let's unpack. This sum goes over all subsets of 1 through n that are not empty. I need to tell you how to add 2 polytopes together. Okay. So in general, if S and T are just subsets, say R to the n, you should think about S and T as being polytopes. S plus T is the thing you would guess if you're on an exam and you didn't remember. Little s plus little t, or little s in S and little t in T. So P1 plus P2 looks like well, there's an origin in here, so if I add that to everything in P2, I'll just get this chronicle again. But then there's the second standard basis vector. If I add that to everything in P2, I'll get these bits, which looks like that triangle just shifted up there. I have the first basis vector. Divide that to everything, then I'll get this polygon shifted to the right. And I've only applied this trick to the vertices of this, namely the origin and each of the standard basis vectors. But if I tried anything else in here, it would be in the convex hole of those situations. So that is P1 plus P2, right? And what do? You take one of these polygons and you just pick up your favorite point, mine was the origin, and you just drag it along the boundary of this polygon. That's the easiest way to like visualize and do this. Otherwise, go ahead and add infinitely many pairs of numbers together, your choice. If you'd like, it's the convex hull of the vertices set. So this will give you a finite algorithm at least to do it. Okay. So what is this formula for two polygons? It's just the volume of P1 plus P2 minus the volume of P1 minus the volume of P2. And this is kind of one of those formulas where it's easy to just see examples and you know exactly. If we had 3, then it would be the volume of P1 plus P2 plus P3 minus the volumes of all the pairwise sums plus the volumes of all the singletons. It's this alternating inclusion-exclusion formula, essentially. Okay. So let's do it. The volume of this, so I'm really bad at my like high school, grade school geometry. So I'm just gonna like bust things up into squares, which I know have area 1, 2, 3. There's a 1 by 2 right triangle that has area 1. This triangle and this triangle together give me 1. Sorry, maybe I should just write the 1s everywhere. Count the 1s. That's a 1. So I got 1, 2, 3, 4, 5, 6. 6. Okay. Minus the volume of P1, which is 1/2. Minus the volume of P2, which is 1/2.
So I think she's 5, not 6.
Oh,
There's the two triangles that you put 1 on, but it's because together.
I didn't put a 1 on this one. So this is a square, this is a square, this is a square, that's 3 here. This is a square, that's 4. This is a 1 by 2 triangle, that's 5. And I still have these 2 bitty triangles.
Okay.
The 5 plus 1/2 plus 1/2. P1 is 1/2. P2 is 1/2. Yes, that's cool. Okay. So this tells me that the generic number of solutions to this polynomial system is 4, which is pretty cool. Gives you a combinatorial formula for computing these things. Questions? There remain open questions about structure of systems like this. If you're really into this story, check out the famous GKZ book, GKZ, maybe, Gelfand, Kapranov, and Zelvinsky, where they tell you all about the deltas that appear for such systems. They're called A-discriminants. Open question is to compute the Galois groups of these things, which we'll talk about. Enter. On your homework for next time, you will compute a mixed volume. You will verify that that is the correct mixed volume by solving one of these systems. You know, everybody always thinks combinatorics implies other subjects, and that like we should reduce things to combinatorics because combinatorics is easy. But just as much other subjects imply combinatorial things, which may be very difficult in combinatorial land, but very easy in geometry land. Okay, so if you wanted to compute a mixed volume, you could do what we just did, or you could go into Julia and solve a random system that looked like that. Two sections from now is the beginning of our discussion on witness sets, witness supersets, which are the super witness sets. And so I just wanted to anchor these right now. the starting point for one of these systems is a polynomial system, which is not parameterized, but is also not squared. So if I have fewer polynomials than I do variables, I should expect lots of solutions, big dimensional solutions. For overloading notation here, you will have to forgive me. It should be clear from context. So I'm going to use delta to refer to. Right, 1 second. Let's say something correct. Refer to the standard full dimensional simplex in R to the n. Okay, the standard simplex in R to the n is usually just a convex hull of the standard unit, standard basis vectors. But then, for example, in R3, you would just get this triangle. I want the full dimensional one, so we're going to take the origin also in our vertices. Okay. So we're gonna take the system we had before, and so this one doesn't depend on parameters. But the polynomials we're gonna include will depend on parameters, these PR alphas. And it's gotta go up from 1 to n minus 10. Y'all call it WN. Okay, so now we are in the situation that we had all day. We have a square system, depends on parameters and variables. What does it represent and who cares? And of course I can do this. Where's the motivation, Taylor? Let's do an example. Favorite one. In 3 dimensions. This. The unit sphere center of the. Henceforth will be called the sphere. What's WF? Well, we have the defining equation of the sphere. I'm going to use a. It doesn't matter what notation you give the parameters. If I fix parameters here generically, how do I geometrically interpret the solution set? It's an intersection of things because I've just listed 3 things. One of those things is the sphere. What are the other two geometric objects I'm intersecting with?
Hyperplanes.
Hyperplanes, perfect. Let's combine these together first. What does the intersection of two random hyperplanes look like?
Line.
A line, perfect. And so I'm intersecting the sphere with a line. I get 2 points. All of this information encoded in a parametrized polynomial system like this is going to be the main object of numerical algebraic geometry. It's called a witness set. More technically, it's a witness superset for the union of the top dimensional components. So for example, I could have written the union of two spheres and done this, right? I could have made a variety that has many different dimensional components. You know, and then only some of those are going to be seen by including these linear sections, namely the top dimensional ones. Okay. Or the bottom dimensional? The lowest dimensional ones? Maybe. Okay, one of those. My brain's not working. And this parametrized polynomial system will be the main topic of the witness set section, which is the longest section also. The basic idea is that so far, all we've ever discussed is solving systems which generically have finitely many solutions, which is not a very versatile thing to be equipped with if you're interested in positive dimensional solution sets. And so you do the thing mathematicians always do, which is if I find something that's harder than what I know how to do, I just massage it until it is something I know how to do, right? So spheres, yeah, I can't really represent that on a computer so well. I mean, I can write down the equations, you know, but that's a different area of math. I want to do this geometrically. So I'm just going to slice a bunch of times until I do a finite. And that's going to be how I represent the sphere. Not just by these points of intersection, but these points of intersection with the ability to now move in the parameter space. Right? I can move that line around as much as I want. And that is where the power of numerical algebraic geometry is, the ability to move around. Okay? So for example, you can sample points very easily. Solve this for like 1 billion different lines. You have 1 billion different points. You can do variety inclusion tests, which means you can do variety equality tests. You can do an immense amount of things with witness sets. And really at the top level, numerical algebraic geometry is the study of trying to extract information about varieties from these witness sets. Okay, that's class. Thank you.